National Electrical Code Section 430.27 states that the total load served by a feeder protected by an overcurrent device shall not exceed the product of the permitted ampacity of the feeder conductors, the number of conductors, and the factor of diversity used in determining the feeder ampacity. To apply this rule, consider the permitted ampacity of three-phase feeder conductors for a 200 amp panel, which is 200 amps. The number of conductors in a three-phase system is 3. Factor of diversity as per National Electrical Code Section 430.27 subsection C for residential loads is 1. Therefore, the calculation is 200 amps multiplied by 3 conductors multiplied by 1 for diversity, equaling 600 amps. Therefore, the 200 amp distribution panel could theoretically supply the load for up to 6 100 amp subpanels because 600 amps divided by 100 amps equals 6. However, the National Electrical Code also requires that the load on a feeder not exceed 80% of its rated ampacity according to National Electrical Code Section 430.22. Therefore, in practice, it is recommended to limit the number of 100 amp subpanels to 5. 200 amps multiplied by 0.8 representing the 80% rule equals 160 amps. 160 amps divided by 100 amps equals 1.6 subpanels. So, the conclusion is 5 100 amp subpanels, not 1.6 subpanels. As a best practice, it is advisable to consult with a licensed electrician to evaluate the specific circumstances and determine the maximum number of subpanels that can be safely fed from the 200 amp distribution panel. This will ensure compliance with electrical codes and prevent potential safety hazards. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations in the United States. It is developed and updated by the National Fire Protection Association, or NFPA, and is widely adopted by state and local jurisdictions for ensuring the safety of electrical systems. The NEC covers various aspects of electrical wiring, equipment, and installations, aiming to minimize fire and electrical shock hazards. Key areas covered by the NEC include wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It provides specific requirements for conductor sizing, circuit breaker and fuse ratings, grounding electrode systems, and the installation of various electrical devices and appliances. Compliance with the NEC is crucial for ensuring the safety of people and property, and it is typically enforced by local electrical inspectors. Regular updates and revisions to the NEC reflect advancements in technology and address emerging safety concerns, making it an essential resource for electricians, contractors, and other professionals in the electrical industry. Understanding the NEC is critical for safe and compliant electrical installations. Ampacity is the maximum amount of electrical current a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. It is a fundamental concept in electrical engineering and is essential for ensuring the safe and reliable operation of electrical systems. Ampacity is determined by factors such as the conductor material, size, insulation type, and the surrounding environment. Conductors with higher ampacity can handle larger amounts of current without overheating, which can lead to insulation breakdown and potential fire hazards. The National Electrical Code, or NEC, provides detailed tables and guidelines for determining the ampacity of various types of conductors based on these factors. When selecting conductors for a particular application, it is crucial to choose a conductor with an ampacity that meets or exceeds the calculated load current to prevent overheating and ensure the safety of the electrical system. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in the event of an overload or short circuit, protecting conductors and equipment from damage. Properly sized conductors and overcurrent protection devices are essential components of a safe and reliable electrical system. A feeder in electrical systems is a set of conductors that originate at a main power source, such as a service panel or a distribution board, and extend to one or more branch circuits or subpanels. Feeders are responsible for carrying a significant amount of electrical current and are typically larger in size than branch circuit conductors. The primary function of a feeder is to supply power to multiple loads or areas within a building or facility. Feeders are designed to handle the combined load of all the branch circuits they serve, taking into account factors such as demand factors and diversity factors to ensure efficient and reliable power distribution. Proper feeder sizing and protection are crucial for preventing voltage drops, overheating, and other electrical hazards. The National Electrical Code, or NEC, provides detailed requirements for feeder sizing, overcurrent protection, and installation methods to ensure the safety and reliability of electrical systems. Feeders play a vital role in the overall electrical infrastructure, providing the necessary power to support various electrical loads and equipment. Overcurrent protection is a critical safety feature in electrical systems designed to protect conductors and equipment from damage caused by excessive current flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to automatically interrupt the flow of current when it exceeds a predetermined level. This prevents overheating, insulation breakdown, and potential fire hazards. Circuit breakers are resettable devices that trip open when an overcurrent condition is detected, while fuses are one-time devices that melt and break the circuit. The selection and sizing of overcurrent protection devices are based on the ampacity of the conductors and the characteristics of the equipment being protected. The National Electrical Code, or NEC, provides detailed requirements for overcurrent protection to ensure the safety and reliability of electrical systems. Proper overcurrent protection is essential for preventing electrical fires, equipment damage, and electrical shock hazards. An electrician is a skilled tradesperson who specializes in the installation, maintenance, and repair of electrical systems and equipment. Electricians work in a variety of settings, including residential, commercial, and industrial buildings, ensuring the safe and efficient operation of electrical systems. Their responsibilities include reading blueprints, installing wiring and conduit, connecting electrical fixtures and equipment, troubleshooting electrical problems, and ensuring compliance with electrical codes and regulations. Electricians use a variety of tools and equipment, such as wire strippers, pliers, multimeters, and conduit benders to perform their work. They must have a thorough understanding of electrical theory, wiring methods, and safety procedures to prevent electrical shocks, fires, and other hazards. Electricians typically complete an apprenticeship program that combines classroom instruction with on-the-job training. They may also be required to obtain a license or certification to work in certain jurisdictions. Electricians play a crucial role in ensuring the safety and reliability of electrical systems, and their expertise is essential for modern infrastructure and technology. Electrical safety is a paramount concern in all aspects of electrical work and equipment operation. It involves implementing measures and practices to prevent electrical shocks, burns, fires, and other hazards associated with electricity. Key electrical safety principles include proper grounding, insulation, overcurrent protection, and the use of personal protective equipment, or PPE. Grounding provides a safe path for fault current to flow, minimizing the risk of electric shock. Insulation prevents contact with live conductors, reducing the potential for electrical accidents. Overcurrent protection devices, such as circuit breakers and fuses, interrupt the flow of current in the event of an overload or short circuit. PPE, such as rubber gloves, safety glasses, and insulated tools, protects workers from electrical hazards. Regular inspections and maintenance of electrical systems are essential for identifying and correcting potential safety issues. Electrical safety training and awareness programs are crucial for educating workers and the public about the risks associated with electricity and how to prevent accidents. Compliance with electrical codes and standards is also essential for ensuring electrical safety. By following these principles and practices, the risks associated with electricity can be significantly reduced, creating a safer environment for everyone. A distribution panel, also known as a breaker panel or electrical panel, is a critical component of an electrical system that serves as the central point for distributing electricity to various circuits within a building or facility. The distribution panel receives power from the utility company or generator and distributes it to individual branch circuits through circuit breakers or fuses. Each circuit breaker protects a specific circuit from overloads and short circuits, preventing damage to wiring and equipment. Distribution panels are typically located in an accessible area, such as a utility room or closet, and are labeled to identify the circuits they control. The size and capacity of a distribution panel depend on the electrical load requirements of the building or facility. Proper installation and maintenance of distribution panels are essential for ensuring the safe and reliable operation of the electrical system. The National Electrical Code, or NEC, provides detailed requirements for the installation, wiring, and protection of distribution panels. Regularly inspecting and testing distribution panels can help identify potential problems such as loose connections, corroded components, or damaged circuit breakers, which can be addressed to prevent electrical hazards. Distribution panels play a vital role in the overall electrical infrastructure, providing a safe and efficient means of distributing electricity to various loads and equipment.